Alright, so good afternoon, everyone. I hope I am visible to you and I am also audible to you.
Yes, sir.
Yeah, fine. Okay, so let's start. So I'll be sharing my screen. Okay, so is my screen visible?
No.
Okay, 1 second. I don't know what happened. Share screen. Okay. Okay, 1 second. I guess there is some problem. Yeah, so is my screen visible now?
Yes.
Yes.
Yeah, sorry for the delay. There was some problem. I don't know at my end. So anyway, so I guess it is fine now. So let's proceed with today's content. So yeah, so this course is analog IC design. One second. Yeah, this course is analog IC design, and the instructor for this course is Dr. Shankaran Aniruddhan, and he is a professor in IIT Madras. I am the tutor for this course, and my name is Mayank Anupam. I am a PMRF scholar, and currently I am a PhD student in the E department at IIT Kanpur. Fine. So I hold these discussion sessions or problem solving sessions for your benefit. So for this course. Anyway, so in this week, in the last week content that was delivered to you, uh, you saw about, these things, right? So frequency response of the amplifiers and basically small signal gain and other things. So was the content clear to everyone? Is there any doubt in that, content wise? Okay, so fine. That no response means no problem. Okay, so today I'll be solving some questions. I'll be solving some questions based on concept that was delivered, and I want you to help me solving this question. Fine. So let's solve the first one first. Okay. So yeah, I want to find the small signal gain between this input to output. Okay. So let's solve it. Let's do it. And for all these questions, ignore this thing. Ignore uh, body effect. Let me change the color. inner body effect. Okay, but yeah, you have to consider channel length modulation. But consider CLM. You all are familiar with this, right? Channel length modulation and body effect. Everyone.
Yes, sir.
Fine. So let's solve the first question. So what is question number? This A part is, this is the circuit, right? You have PMOS, then you have a PMOS. Oh, sorry, you have PMOS again here. This is VB3. This is VB2. Okay. This is M3. This is M2. And then what you have? You have this NMOS. Then you have this input V in. You have some bias here, VB1, and you have this output V out. Okay. So now tell me, how do I find the small signal gate between this input and output?
Sir, this is a common gate configuration.
Okay.
So the upper two MOSFET make a cascade load.
Okay. So this you are saying that it's a cascode load, right?
Yes, like a RS we can say.
Okay. Fine.
Okay.
Fine.
Then the simply the gain is we can use the formula 1 over 1 plus GM or not. This that formula.
No, no. I didn't understand that formula. So can you tell me what it is?
Sir, for common gate, the gain is like a plus GM or not for a simple uh, CG stage.
Mm-hmm.
Okay, so here R naught is the
Okay. So
uh,
okay. Fine. Fine. So this is basically you remember this, right? So I want you to solve it. Okay. I want you to solve it properly. So anyway, so let's forget about this. Today I will be I want you to I want to explain you one of the methods to find the small signal gain. Okay. So one method to find small signal gain is, right. What do you do? So you simply one second. You will simply solve the whole circuit, right? Okay. You'll simply solve the whole circuit between input and output. We basically you'll solve the whole circuit by making it small signal equivalent, and then then writing KCL and KVL, and then finding the relation between V out and V in, right? That is one way. But there is also another way which also can be used. So what do we do in that is, we we find out, one second, we find out, this is basically a approximation. Okay, this is basically an approximation which works almost in all the cases. There are some cases where you will have to be careful. Actually, it will always work. There's no, it's not like an approximation, it will always work, but you'll have to be careful while using this. So but in this case it can be easily used. So what it is that for any circuit where you want to find out the small signal gain, for any circuit where you need to find the small signal gain, uh, you can use the following method. What is it? So what do we do is, basically we have an input and output, right? So what do? We do two things. First, first step is first step is short the output. Okay, short the output and calculate the small signal, this thing, uh, small signal short circuit current. due to the input voltage. Okay, so what do I do? First thing, so in this circuit, the circuit that is here, what do I do first? I first short it. The output is shorted at first. Okay, this two are left as it is, and then this guy is shorted here, and then we have this NMOS, right? And we have this input. This is VB1. Oh, by the way, all the biases are also grounded, right? These are also shorted because we are talking about small signal. Okay, so for the first case, what do? We short this place here. Okay, and here we shorted it. Okay, and now because of this input voltage, we find out how much current is flowing into the short circuit ground. Okay, so this is called ISC. Okay, this is ISC. So basically we have to find ISC. This should be small. We have to find ISC by V in. Okay, and that will give us a GM, which is the equivalent GM of the whole circuit. Okay, this will give us a transconductance of the whole circuit. So because of this input voltage, how much short circuit current is flowing? So that is first we have to find out. So what will that be in this case? What will that be? This is M1. Okay, this is
Just
M2.
simply GM1. Like,
Correct, correct,
yes.
correct. So here the short circuit current ISC by V in will simply be equal to what? GM of 1, right?
Yes, sir.
Correct. Now this is the first step. Now second step, we find the we short the input. Okay, we short the input, uh, short the input, and find the output resistance. Okay, let's call it some R out. Okay, and let's let's call the first one, let's call it ratio C by V in some GM equivalent. Okay, fine, and let's call it R out here. So for the next step, what do? We simply find out the output resistance. So let's copy this guy here, copy and then paste it here. Okay, now let's find out. We have to short it, right? We have to first short this guy here, and this we should not short here. Now we have to find the output resistance here, R out. So what will the R out be in this case?
Sir, RO1 parallel
Yeah,
1
so
plus GM2
GM1
RO2.
is equal to RO1 parallel, and the cascode of this, right? So
Yes, sir. Yes.
approximately how much that is equal to GM2 times RO2 times
RO3.
RO3, right?
Yes. Yes.
Approximately. Fine, fine. So that is R out. And now third step, the small signal gain is equal to what? Simply equal to GM times R out. Sorry, GM equivalent times R out. Okay. So what will it be in this case? So in this case, the gain is what? GM equivalent is what? GM1, right? This is GM1. So it is equal to GM1 times RO1 parallel GM2 times RO2 times RO3, right?
Yes, sir.
Yeah, so this is a very nice way to find the small signal gain in which you can decouple the things. I mean, uh, instead of solving the whole circuit, you can solve it part by part. I mean, first you can calculate small signal current, short circuit current, and secondly you can calculate the uh, output resistance, and then you can simply multiply them, and that will give you the small signal gain. Okay, fine, fine. So this we understood, right? Now let's quickly cross-examine it by solving the whole circuit. I mean, let's see whether it is correct or not. So we have this circuit, right? We have cross-examine the method. We have this circuit. Fine. Yeah. So what will be the small signal equivalent? So basically, you can this whole cascode load, we can simply represent it in terms of R out, right? Basically the equivalent resistance of this. So this here, this cascode load here, it does not carry any signal, right? Any current, anything else. It just acts as a load, isn't it? So in the small signal picture, I will simply represent it as a load. So this I can lump as a load. Let's call it R cascode, R cas. Okay, I'll simply represent it as R cascode in the small signal picture. So how will the small signal equivalent look like? So small signal will look something of this kind. So we have this V in, right, at the source. So let's write. So BV1, this will be shorted, right? So gate is shorted here. Gate is shorted. Okay, gate is shorted to ground like this, and we have drain, and in between drain and source we have this current source, and this is the source. Fine. At the source you have applied a voltage source here, V in, correct? So this is gate, this is plus, this is minus. Let's call this VGS. This is GM times VGS. Okay, and this is drain here, and at the drain, at this point here, at this drain, sorry, not this, but this, at this drain here, at this drain here, we have R cas, right? This cascode load here, and what else? The output resistance of this also, right? So at this point we can write RO1 between source and drain of this, which is RO1, and then there is R cascode, correct? Fine.
Yes, sir.
So yeah, and where is the output now? Output is here, right? Fine. Now let's find out what is the small signal gain. Yeah. So what will be the small signal gain here? Let's solve the circuit. So, oh, sorry. Okay. So whatever current goes inside here, I, okay, same current will flow here also, I, right? Is it visible? Is it okay?
Yes, sir.
Yeah. So let's solve it. Yeah. So now, cool. So and I will be equal to what? So this is V out, and let's call this VS. Let's increase this one. So this is V in. This is source terminal. Okay, this is source terminal. So we will call this as V So this is Vs, right? This is source terminal. So what is the voltage at source? It's simply equal to V in, right? Fine, cool. And what will be the now I will be equal to what? This current that is leaving here. This current will be equal to what? This current, right? And what will that current be equal to? I should be equal to Gm times V in, right? Plus what?
V in minus V out by R1.
Correct, isn't it? Right? And this same current should be equal to what? V out by,
R cascade.
correct, right now. So I will be equal to sorry. So in this you can see this two you can take together and you will get what? Gm times RO1 plus 1 divided by RO1 times V in is equal to V out parallel combination of R gas parallel RO1, right? Okay, so maybe I should do this will be like this RO1 plus 1 by R gas, correct? Is it fine?
Yes, sir.
Yeah. And what will that be? So V out by V in will be equal to how much? So it will be equal to R gas code uh, 1 by R gas code plus 1 by RO1 divided by Gm RO1 plus 1 divided by RO1. Fine? Fine? And how much will this be equal to? Is it correct or have I made some mistake here? Is it correct or have I made any mistake here?
Sir, numerator and denominator will be opposite, right?
Correct. Right. Yeah, so why are you not paying any attention? I mean, I'm deliberately making mistakes to see whether people are listening or seeing or not. So if I make something here and there, just interrupt me there itself. Okay, you should be attentive. Yeah. So it will be what? Gm times R naught 1 plus 1 divided by R naught 1 divided by 1 by R naught 1 plus 1 by R gas. Right? Fine. And this can be further simplified into, so let's simplify this will be of R gas code plus R naught 1 divided by R naught 1 into R gas code. Fine. Okay. And this is equal to Gm plus 1 over R naught 1 into parallel combination of, so basically this is parallel combination of what? R naught 1 parallel R gas code, isn't it? Right? Right now, is this clear?
Yes, sir. Yes, sir.
Yeah. So this is what we are getting here, right? Gm plus 1 over R naught 1 into R naught 1 parallel R cascode, and here we are getting only Gm 1 times R naught 1 parallel R cascode. So basically R cascode is this, right? This is R cascode, isn't it?
Yes, sir.
Hmm. So here we are also getting this 1
Sir,
over R naught 1. So what is wrong?
everywhere it's GM1, no, sir, in the
Yeah,
second
yeah,
one.
yeah. Right.
Sir,
GM1.
normally RO1 is very greater than 1, so the 1
Correct.
over R1 is
Yes.
can be neglected.
Yes. Indeed. Here also, I mean, when we are calculating the short circuit current here, we simply ignored RO1 here, right? Here we didn't take RO1, Actually R01 will be present here also, but and if you take into account the effect of R01, then you will get here also. Here also you will get GM1 plus 1 over R01. Okay, but we simply didn't take into account R01, and that is why we were getting this value. So if we take R01 here also, we'll get that. So basically this is the correct method, right? This method that we just devised, this simply finding short circuit current and then the output resistance, that also works. Okay, as can be evident from the fact that when we cross examined using the actual method to find the small signal gain, we get the same answer, right? Hello.
Yes,
Yes,
sir.
sir.
Yes,
Yeah,
sir.
fine. So this will come in handy. Okay, so this method is very powerful. I mean, this will come in handy because calculating short circuit current and output resistance are two different things, and separately they are easier than calculating the this thing full-fledged method. Okay, this is the conventional method to find the small signal voltage gain, and this can be slightly tedious at times, but this short circuit current and this output resistance, they are not so difficult, and you can calculate it many times simply in your mind. So this will come in handy. Fine. So now we learned this, right? Now let's use this on some other
Sir,
topic. Yeah.
the first step in the shortcut method, can you tell how ISC by V out is GM1?
IC by V out is GM. No, no. IC by V in is GM.
Sorry, V1, yeah, yeah.
So is so. And do I need to explain or is it understood?
No, sir, I was not able to solve it to be GM1.
Okay, okay, okay. Fine. So see, this is V in, right here,
Yes, sir.
right? And what do we need to find out? This output current ISC, we have to find out ISC by V in. Okay, so because of this V in, what will be the output current? So forget this R01 for time being. So you see that this is shorted. Okay, this terminal is shorted, this terminal is shorted here. Okay, this is simply grounded. Okay, this terminal is also grounded. And what is the current that will be flowing in this MOSFET small signal current is equal to what? GM times VGS, isn't it?
Yes, sir.
And the direction of flow is what? In this direction, right? Downwards.
Yes, sir. Yes, sir.
Correct.
Downwards.
Correct.
Yes, sir.
But now
Yes, sir. Yes.
VG is 0. So VG is 0. GM times GM1 times VG is 0. Oh, anyway, so first thing, this current and this current will be equal, isn't it? ISC has to be equal to this current.
Yes, sir. Yes, sir. Yes, sir. It's
Correct.
grounded. Yeah. Yes, sir.
So now GM1 times VG is 0 and VS is what? V in, isn't it?
VN.
Correct.
Yes, sir.
Yeah. So what is the this current? This downward flowing current is minus GM times V in, right?
VN.
Correct.
Yes, sir.
And this current direction is downwards, but ISC is flowing in
Downwards.
this direction, right?
In that. Yes,
So
understood.
it will be
Understood.
positive here.
Understood.
Correct now?
Yes, so that those two MOSFETs are grounded, so either ways VGS is zero. Understood.
Yeah, right. So this is anyway not going to contribute. These two are not going to contribute. Okay.
Yes, yes, understood. Thank you, sir.
Yeah, yeah. Cool. So let's fine. Let's solve another question. So which one would you like to solve?
Sir, H.
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 Okay. Okay. Cool. So this is the H one. So let me remember the circuit. Okay. So this is a folded kind of thing. Fine. So H part, we have this MOSFET, and then we have another MOSFET here which is connected. Then we have another MOSFET here, right? PMOS. Okay, this is a PMOS. Its gate is strapped like this. Yeah, let's train this to VDD here. what is this? It's current source. We have this input here. Okay, this is M2 and this is M3. Yeah, so instead of me doing, I will ask you to do it. So tell me, how will you do it? Yeah, yeah. So tell me.
So for first V out will be shorted.
Okay, first
And
Vout is shorted. So let's do it. First step, find short circuit current at the output. So first let me take this circuit here. Okay, and let me short this guy here. Okay, and we have to find out this ISC, isn't it? Because of this V. Yeah, so what will it be?
Sir,
Yeah.
the voltage at drain of M1 will be just again will be GM on into RO3 into V in.
Nothing. What are you saying?
Sir, node voltage of M1 at drain.
Yeah, this drain voltage. Okay.
This will be like minus GM on RO3 into V in
Minus GM1 times RO1 and
into V in
into V in and
and and that is it.
are you sure?
sir, RO33 must be included and
Correct.
parallel to RO.
Yes, 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 yes.
Right now.
And yes, sir.
So this is not true, right? Because this is when this is grounded, so this is also grounded, right? Now this is
Yes.
very easy to see. Now everyone can solve this, isn't it? What is the short circuit current now?
That quantity multiplied by GM2.
Right now,
Yes, sir.
correct. So what is GM equivalent? It's equal to what? ISC divided by V in, correct? This is equal to what? Minus,
GM1 GM2 into R1 parallel R3. Yes.
right? Right?
Yes, sir.
Correct. And now next step. Second step, what do we do? Again we take the circuit and now do this, right? Open this, correct? Now we have to find out
Yes.
the output resistance, right? R out. So what will it be?
So 1 by GM2.
Just 1 by GM2 or anything else? Or will it be complicated? I don't think it will be 1 by GM2. Will it be? Will it be 1 by GM2?
Yes, sir. It is coming to 1 by GM2
Yes,
only.
sir. Yes, sir. On over GM2. Yes.
How did you find out? So let's solve it. Okay, let's see whether it is coming out to be 1 by gm2 or not. Okay, so small signal, what will you do? What will I do for finding out? I'll simply put a voltage source here, some V test, correct? Find out how much is the current I test, right? So because of this V test, this node voltage is also V test, right? I mean this gate voltage is V test, isn't it?
Yes, sir.
Correct?
Yes, sir.
Let's ignore R out of all the devices in this case. Okay, let's ignore R out. Ignore R out of all the devices. Fine. So yeah, now because of this V test, this voltage also will be V test, isn't it? Okay, so let's call this voltage as some Vx. Okay, so if we are ignoring R out of all the devices, so this device is out of picture, right?
Yes, sir.
Correct. So if this is Vx and this is V test, so what is the current that is going to flow in this right here? This will be Vx minus, so let's call this current as I. This current will be anyway I test, right? This current is I
Yes.
test.
Yes.
Sorry, minus I test, isn't it? Right?
Yes. Yes. Yes, sir.
Yes,
Now
sir.
this is Vx minus this is V out, V test, right? V test times Gm of 2 should be equal to what? I test minus I test. Correct? Correct now?
Yes, sir.
Correct. Okay. Okay. 180 okay.
Sir, one thing can I say
Yeah, say.
like M1 is off
Hmm.
and the current from V test to the M3 is zero as
Yeah.
it is at connected to the gate.
Hmm.
So no current can flow through M1 and M3
Yeah, so
and
as you
only
can
M2 is the current through path.
cannot ignore that. Okay, cannot ignore this. So assume there is some resistance here.
Okay, okay.
Fine. Yeah. Now tell me. So what will be Vx? Vx is equal to Gm of 3 times V test
Arrow
times RO1, and will it be minus or plus?
minus.
Correct. Right now?
Yes.
Yeah, so now let's put it here. So what will you get? Vx, so this will be minus Gm3 times RO1, okay, uh, and minus 1 times Gm2 times V test, correct? Is equal to minus I test, right? Right?
Yes.
Yeah, and what will it be? So it is I test by V test, or let's do the other way around. V test upon I test is equal to what? What?
GM.
1 plus Gm3 times RO1, isn't it?
Yes, sir.
Yeah, so you were saying it is only Gm1 over Gm2, right?
Yes, sir.
But it is much more than that, isn't it? Much less than that. It is much less than that, isn't it? You see, Gm3 times RO1, this M3, and the gain of this, if the device gain, if the gain of GM3 is much, if gain of M3 is much very large, then this V test by I test will be much smaller than GM3 1 over GM2, isn't it? You see, this is further divided by a factor. This is supposed to be large factor. Okay. By the way, do you identify that there is something weird going on here? I mean, what is happening here? What is this connection? What is this connection here? This is a feedback, isn't it?
Yes, sir.
You see, how is the feedback action going here? Going on here? Tell me. What is the feedback action? How is the feedback? What is first of all? What is this feedback kind of? Is it positive? Is it negative? What is it? Is it a positive feedback or is it a negative feedback? Tell me.
Negative, negative.
How? Why
Negatives.
do you say that?
Sir, if we increase the V out, like
V
V
out.
test,
V test. Okay.
then the gate voltage of M3 is increasing,
Increasing. Okay.
and the output of the drain of M3 is decreasing.
Correct.
And the if and M2 is in the common follower,
Correct. Yes.
short
Yes. I
follower.
I get it. Yes. So this should go down, isn't it?
Yes, sir.
So basically,
So, or even just from the equation, Vx will decrease whenever V test increases.
right. Right. Exactly. Yeah. Yeah. So equation tells everything, but I want to see whether you can reason it out or not. So that other person, his reasoning was correct. So you have to see whether if at one side of the uh, at one point in the loop, if you increase or decrease, if you give some excitation, the return of that excitation should be opposite of that, should be of opposite sign, isn't it? Then we can say
Yes.
that it is negative feedback. So it is a negative feedback. And what is this negative feedback ensuring, by the way? What is the purpose of this negative feedback? So let's see this figure, right? This is the figure, actual figure. So what is the purpose of this negative feedback? What is this ensuring?
Well, as it is a voltage amplifier, so the output resistance will be less in feedback.
Correct. So what is the purpose? I mean, no, resistance is less, I understand. But okay, so okay, you are saying that it is a voltage controlled voltage source. So that is why
Yes,
it's
yes,
okay,
yes.
yeah, correct. So that is one of the way to say it. Now, can you tell me what is another way to look at it? I mean, uh, how do I explain? From the perspective of R out only. So yeah, so you were right actually. So yeah, that is actually the way to look at it. The R out, it is actually a way to reduce the output resistance. Okay, when you put it in feedback, you have simply reduced the output resistance, and that is why it becomes a very good
Voltage source.
voltage
Like,
source, voltage controlled voltage source, isn't it?
yes, yes, yes.
Fine, fine, nice. So yeah, so what is so this is the this thing R out. Okay, so what is the gain? V out by V in, step 3 should be equal to what? This is GM equivalent, isn't it? Correct.
Yes, sir.
So this is minus GM1 times R naught 1 parallel R naught 3 into GM2, and divided by the this gain, right? This R out. So R out will be GM2 into 1 plus GM3 times R naught 1 parallel RO 3, isn't it? Yeah, so here we ignored the output resistance of M3, but if we had taken output resistance of M3 also, then this would have been simply parallel, right? Isn't it? You see RO1 here and RO3 here,
Yes, yes, parallel. Yes, sir.
they will simply be in parallel, correct?
Yes.
Yeah. So this is it. Simply, so GM2 and GM2 are gone. So what is it? Minus GM1 times R01 parallel R03 divided by 1 plus GM3 times R01 parallel R03. Correct? Fine?
Yes, sir.
Yeah. So I guess you can solve it now, right? All the questions. So I would encourage you to solve this circuit, this H1 V out by V in, from the conventional method also. You cross examine using this conventional method. Okay. You write KCL and KVL and then solve it, and then see whether it is coming to be the same or not. Okay, so exercise for you. Uh, Solve H using conventional. Okay.
Hello, sir.
Yeah.
Sir, okay, can we intuitively derive the topology of H? Like if we want allowed to be very negligible, so how can we intuitively come out with the topology?
Yeah. See, in general, this is a principle in feedback. Okay. Let me use this color. In general, it is a principle in negative feedback that basically the resistance at all the nodes in a loop goes down by a factor of loop gain. Okay, so what do I mean is by this is that whenever you have a suppose, okay, so let's see this question. If you didn't have this connection here, okay, if you didn't have this connection here, and let's say this was simply connected to some VB, okay, is this visible by the way?
Yeah.
Yes, sir.
If this was simply connected to some VB, then you can see now that this is a this is a simple amplifier, right? Two stage amplifier. The first is common source, this is common source stage, and this is a common drain, right?
Yes, sir.
Right now, so this is a two stage amplifier, correct? Now what we have done is we have simply connected it in feedback, right? And by the way, this two stage amplifier, this first stage is common source, right, and this second stage common drain. The output resistance of this common drain is what? The output resistance of this amplifier is what? Simply 1 over gm2, isn't it?
Yes, sir.
When this was not there, when this connection was not there. Okay, now what do we do? What did we do? We simply added this negative feedback connection, right?
Yes, sir.
Yeah, because of this negative feedback connection, this output resistance of this guy here, output resistance, it went down by the factor of what? Loop gain. What is the loop gain by the way in this case? Where is the loop? This is the loop, right?
Between- Yes, sir.
So what is the loop gain? It's gm3 divided gm3 times r naught 3 parallel r naught 1, isn't it? Into into what? This is a source follower, right?
So it should be unity.
One in, right. If you ignore body effect, this is a unity, right?
Yes, sir.
Right. So this is the loop gain. GM3 times RO3 parallel RO1, right? So you see
Yes.
this is simply GM1 divided by, sorry, GM2, which goes down by this factor. GM3 times something like this. So let's see whether it is indeed happening or not. Sorry, this is not GM2 but 1 over GM2, which goes down further. It's actually earlier it was 1 over GM2, right?
Yes, sir.
And now it is further divided, so it should be 1 over gm2, which is further divided by this factor. So that is what we are seeing here also.
Okay, sir.
Further divided by
Understood.
this factor, right now.
Yes, sir. Understood.
Yeah, so in general, if you want to make a good voltage source, voltage controlled voltage source, you put things in feedback. in general. Okay, so that is why you see an op amp, it is never used in a in this thing open loop. When you were learning op amp, okay, so this is an op amp which was of very high gain, right? This was a very high gain op amp. Okay, now what did you do? You put it in negative feedback in this manner. Let's not talk simple voltage controlled voltage source. Let's take this two-stage Miller compensated op amp. Okay, so you don't use it in simply like this. You put it in negative feedback, right? Like this, isn't it? Now when you put it
Yes,
in
sir.
negative feedback, what happens is that the output resistance here, it goes down. It simply becomes 1 over gm. Sorry, 1 over gm. Okay, otherwise without this connection, the output resistance is infinity, isn't it?
Yes, sir.
But when you put this connection here, this goes down. This becomes 1 over gm. Okay,
Yes, sir.
so in general, when you want to reduce the output resistance, you put it in negative feedback. Not only output resistance, but any resistance, any high impedance node will become low impedance node when you put it in negative feedback. Okay, so that is the intuition.
Yes.
Fine. So I guess you can solve any question in this little series of question here. Fine.
Sir, one doubt, sir.
Yeah.
Sir, regarding the negative feedback, sir, V test increases, the VG increases, therefore ID decreases, which decreases in the VD of that
Which where are you actually?
negative feedback, sir.
Okay, let's. So this is negative feedback, right?
Yes, sir. V out increases,
Uh,
so uh, ID decreases.
where is ID?
ID of M3, sir.
M3. Yeah, correct. It decreases. Yes.
Uh,
I3 decreases.
so that VD also decreases, VD of M3.
Correct. It also goes down, right?
Therefore, VGS of M2 decreases,
Correct.
so ID decreases, therefore V out decreases. That is the.
Correct. I mean, because this current that is flowing through M2 is constant, isn't it?
Yes, sir.
So if the gate of M2 goes down, and
Yes, sir.
if it has to maintain the same amount of current, then naturally its source has to go down, isn't it?
Yes, sir.
So that is why, that is how this negative feedback is working.
Sir, here in M3, sir, V out decreases, so ID decreases, therefore that VD decreases. Correct
Correct, correct,
assumption.
correct, correct. Yes.
Okay, sir. Thank you.
Yeah. Fine. So let's move on to the second. I will encourage you to solve all these questions. Okay.
Okay, sir. Okay.
Yeah. So just so basically this is a reference is actually Behzad Razavi's book. Okay, so this is actually taken from
Yes, sir.
their exercise only. So if you want, you can solve their exercise. I just took these questions just to solve it here, show how to solve. Fine. Let's take this question. Oh, by the way, this is also the same thing, same old, same old. So, what should we do here? Yeah, so here this is something which where you have to be careful actually slightly. Yeah, so this is slightly interesting. No, yeah, so let's solve this question, first one. Okay.
We record. Like,
Oh, thank God. It is not this thing. It is not gone. It is there.
yes,
So
yes.
what I will do is I will simply do this